Welcome back to the channel and welcome back to this series of videos on my PhD. This is part 2 and possibly the final part for now. I may do a few more later, but I want to tell you about the thing that I didn't tell you in the last video. In the last video, I was telling you about the text and how I reviewed the text of my PhD thesis about 15 years later. In this video, I want to tell you about the code. I think everyone knows that AI can write code and it can write it reasonably well. And in the last video I was trying to argue that AI can kind of do science and to a level that's good. Is it going to be perfect? No, but then humans aren't perfect either. There was times that there were flaws in my PhD, in what I wrote in the thesis, that weren't even picked up by humans, but it was picked up by AI. And so I'm going to go through this video and tell you where we wrote code and we actually diagnosed problems that I had before 15 years ago. I didn't figure them out, but we've got them figured out now. And this is something of a success story for AI within science. So just a reminder, my background and my PhD, I actually have the wrong title here at the top, kind of funnily enough, but just beneath it I actually have the real title, which is the real title page from my PhD thesis. So it is Schrödinger wave mechanics and large-scale structure. If you've watched the previous video, then you'll have some idea of what this means. If you haven't, let me give you a brief recap of what that is. In the picture here on the right-hand side, you have what is meant to be galaxy surveys. So these are images, slices from the data, and each dot is basically a galaxy. That's what I remember them to be. I could be wrong, but I think that's what it is. So these are real observations from our universe. The data is collected by some telescope and then is plotted. And this is a plot of the galaxies. Basically, the further out it's at a higher redshift, and therefore it's at an earlier time within the universe. Obviously, because it takes time, a long time, for light to reach us from faraway galaxies. In the red part, in the lower part of this image, is a simulation. It's actually a cold dark matter simulation, an n-body simulation. Each dot is basically a blob of dark matter. It's not necessarily a galaxy, but you can do some sort of statistical checks, shall we say, or calculations to see which ones are meant to be, like which ones would come together to form a galaxy, shall we say, and you argue. However, they're not galaxies, but you can at least try to look at the distribution of this cold dark matter and say, is it similar to what we see in the universe? Is our model, and it is a model, is the model roughly the same as what we see, or is it completely different? And there's similarities. It's not perfectly the same. And some success of the n-body simulations is that we are getting reasonable agreement, but there are differences. And what I did is I took a different approach using an equation from, you could say, quantum mechanics. The Schrödinger equation is quite famous. And so I'm taking a different approach and doing my simulations using these other systems of equations, which is not an n-body. It's in the maths, it's a continuous field, and although it does become basically discrete, so you have arrays within the code which will hold all of the values, and the arrays basically is like grid points across a 3D grid across the entire simulation. Well, not the best explanation, but that's the sort of high-level overview. So what we did is we had AI to write code. It's going to be C++, so it didn't use my code. It basically has not seen my code at all. We ignore that. And we are going to look at a particular set of equations that I'm going to show you in the next slide. And this was just kind of a fun slide that I made with AI. So these are the systems of equations. For those of you who don't have a maths or a physics background, they probably don't mean a lot to you. You have probably heard of Schrödinger, and Poisson is about gravity. That's the one with the V. So you're taking some second derivative with respect to some potential V. The V is a potential. It's a gravitational potential, and this is a relationship between the gravitational potential and the wave function. At the bottom, we have a particular type of wave function which transforms the Schrödinger equation into an equation for fluid dynamics, basically. So you're saying you've got some sort of fluid of stuff, and a fluid, if I recall correctly, is a generalization of a liquid. It's basically a liquid or a gas. The two will follow some generalized equation, and it can model both. So super high level, that's what we're trying to do. This is what we want to put down into code, and this is what we want to evolve. In what I did 15 years ago, I had quite a few problems. The code worked, but the outputs were messy. The growth stopped, and if you can see from this image here, there's a lot of noise, and it's not really clear what that is. This is not really expected. It's not really what it should be. And my code wasn't really optimized for speed. I wrote it in such a way that I could understand it, obviously, and such that it could just do the calculations, because you have to have something to do the calculations, and so it wasn't optimized. It was just, I needed it to fulfill this function of get me the answer. So with AI, we rewrote the code in C++, as I said. It didn't look at my code. It only used my descriptions in the thesis and obviously whatever's in its training data, and we were able to create faithful representations of what I did before, and the outputs were good. We walked through it step by step. We started with something simple in one dimension with no gravity. We added gravity, we added 3 dimensions, we added co-moving coordinates. So we talk about the expansion of the universe. Well, you also have to add in that expansion into your code, and so that's what we did. Now, this is the interesting part, is looking at the outputs from the new code and then trying to figure out what is it that could be wrong. Because we saw the same problem actually with the new code as we saw in my original code. So it's like, well, probably not my code that's wrong, is it? If we're getting the same results here with this new C++ code. And so here's what we thought about. Could it be that our time steps are too large? And so what if we make smaller time steps such that we get better accuracy in time? And we did that. However, the results weren't really any better, if anything. We then thought, okay, well, what we're doing is in our code, we have a finite difference approach, which will mean something to people who've done this within physics or maths. And we changed that to being a spectral method. So we used FFTs. And this is to solve the kinetic energy operator, which is, you saw in the Schrödinger equation a few slides back, the first term. This may not mean anything to you, but the very first term is the kinetic energy term. And it is tridiagonal. It will maybe mean something to you, it might not. Changing it into FFTs is a little bit tricky, but we eventually did that. However, there still wasn't any change in the results. It still wasn't good enough. And we thought, okay, what if it's one of these strange things where we have a preference to the X direction and not the Y direction or the Z direction? So we basically took the initial conditions and spun them around and then tried to do the calculations along the Y direction or the Z direction. But that didn't make any change either. So it wasn't the data, and it didn't seem to be that we had some preference because of the way that we did the calculations, because in the original calculations we're doing like a finite difference of like this grid element minus a previous grid element and so on and so forth. And we thought, okay, maybe that if you start with X, that would introduce some sort of bias, but it didn't seem to have any difference when we changed things around. So then we're thinking, okay, well, what else can we do? What about the initial conditions? Maybe we have the velocity wrong, or maybe there's something not quite right there. So we set it to 0. And this was interesting because we saw that the growth would still freeze rather than forming the bigger peaks that you would see in an n-body simulation. And that gave us a bit of a hint that maybe something was going wrong. It didn't fully solve it, but it did make us think. And then we were talking more about initial conditions, and we did this round trip test where we took a real initial condition from professional code written by academics, which was Gadget 2 in the past, 15 years ago. This time we've used Gadget 4. And we said, okay, let's take these initial conditions, let's create our wave function from them. So that basically means we would have 2 codes that are different, but have the same initial conditions, and they should step forward in basically the same way. However, with our initial conditions, we found a problem, is that we were losing some velocity, which might sound a bit strange. How can you lose velocity? But we weren't able to represent velocity properly within our representation, as I'll explain. in the next slide. So we were actually losing some information at the start, and then it turned out at the end we're also losing velocity information later on. And I'm going to explain why that is. And this is the problem that plagued me 15 years ago that I couldn't figure out, but I did figure it out with AI through this sort of systematic methodical test. And this has been a real win for AI within science, because I couldn't figure this out. Humans didn't figure it out. We could have maybe figured it out eventually, but we didn't. And it has now been solved, and it was with AI that we solved it, which is great. It was through a lot of back and forth. This isn't like, conversation. It wasn't just AI, snapped its, proverbial fingers and had the answer. No. This is from a lot of testing and a lot of back and forward trying to fix this code. So the root cause analysis turned out to be that we were using up what's called the phase budget, or what we were calling the phase budget. This is where the original transform of the wave function relates the phase of the wave function to velocity, and it's wrapping itself around. Because you've got an exponential, you've got something which is oscillatory, so like sine or cosine, where something like this where it waves, and trying to represent a nice smooth function what we had for velocity from an n-body code, we're putting it into an exponential, and basically it's like wrapping itself around, and that was causing a problem. And we were losing information essentially in that way from the very beginning, so losing 8%. And then later on, because it was wrapping so much, we would lose even more. And so the growth eventually just stops, because the matter can't clump together under gravity because of the fact that we're losing this information, because we couldn't represent it accurately. And this is where there's a key equation. Again, may not mean much to you, but the maximum velocity is related to this phase, to pi, which is just pi, the real pi number, and then the number of grid points of our simulation. So this is n, which in a normal cosmological simulation you talk about the number of particles, and in the wave mechanics version you have the number of grid cells. I was using n of 64, and we bumped it up to 128 to see if we get any difference, and there is a difference. And this is where in my thesis this number was just far too small in order to represent a proper nu value, which should be a sort of classical value because it's related to whether it's sort of quantum mechanics or classical mechanics, and it was causing a problem. And this was basically where we found the problem, is we just needed more grid points for the values of nu that we were interested in, the classical values. So Gadget 4 I just mentioned. Gadget 4 is written by a team of academics in the Max Planck Institute, somewhere in, I think the town is Garking, which is somewhere near what's it called? Bayern Munich, Bavaria, Munich, of course. In English we call it Munich. So they're somewhere near Munich, and they have written this code which is like an industry standard. I compared Gadget 2 with my code 15 years ago, and now I'm doing the comparison against Gadget 4. So we started from the same initial condition, and here we are stepping forward in time. So Z, which is a redshift of 19, and then of 4, and then of 0, and 0 is today. So the top part is Gadget. This is like the industry standard. This is what we should be aiming towards. And my code is on the bottom. Now, does it look perfectly the same? No, it doesn't. But there are similarities, and we did some statistics to show that there are some similarities. It's not completely wild. You will even see some slight strange areas here where we have a sort of interference effect, and this is a quantum mechanical effect. And this is to an extent where the representation isn't quite right, but it does give us a chance to understand the code better, and possibly to even understand the physics better too, is what happens when you make the nu value bigger or smaller, or try to tune it to see if it'll change how the growth is of structure within our universe. Here are some more plots. This is about the density, and yet the density from my code doesn't quite follow the Gadget code as well as it should. And the total sort of maximum peak of density under Gadget 4 does get higher. But that is also a bit of an issue, because Gadget 4 doesn't quite get the same as what the universe has. In fact, in the universe it actually gets a bit flatter, which is a bit like my code. However, the universe is probably somewhere in between, to be honest, rather than it being either of our codes. So this at least gives a hint that maybe what I'm doing here does make sense, or it could give us some extra insights as to what might be happening. So it may not be a quantum mechanical effect, it may just be a real classical effect. However, there may be some insights as to what happens, such as my code has like a pressure term, and maybe this pressure term will cause things to behave in a different way. So cold dark matter simulations are interesting in that they took us from sort of zero to something, but they're obviously not the full picture. And I think that's one of the big takeaways. Not just from my code, but just in simulations of the universe in general. So key takeaways. The method works. We've proven that it works. We figured out what the problem was. It wasn't necessarily the code, but it's choices of parameters. Going for n equals 128 or a bigger number actually makes the code slower. And whenever I was using my code 15 years ago, it was really slow, and I just couldn't quite get it done within enough time. I was kind of struggling to understand all of the effects, and I was afraid I just wouldn't be able to do enough simulations at that resolution to really properly understand. I was just kind of lost. I wrote my thesis, it was done, I had good enough results that we could talk about something, but there was just that one small problem I just never quite figured out. The noise of the plot source, why they're really messy. This was to do with aliasing, this is to do with the velocity, and again to the number of grid points. And it's interesting that my code is a lot faster, but actually my code is much faster because we're not resolving the forces on such a small scale in the way that this Gadget 4 does. While it's got the same number of particles as we have grid points, they do a lot more finer details of the forces of those grid points. So this is interesting because it shows that AI can be a research partner, and we're working at a very fast pace. I managed to do this within a couple of weeks, and again, not even doing it full time. This was kind of like a side project for me, and that has been really interesting. Yes, it is a topic which has been fairly well researched over the last sort of 15 years, certainly more so than the previous 15 years before it, or the previous sort of 20 years before it. But it does show you where AI can be helpful. Will it be helpful going forward in opening up new areas of research? I think some of that's still unknown, but hopefully it will be. It may not give us the answer, but it may give us clues as to where we should look. And I think we're also seeing that in maths and in maths research and in proofs. It's not that AI is necessarily giving you the answer to something completely unsolved, but it's giving you hints for directions that you can look, and then you can try to construct a proof within maths in order to explore this new area. So thanks for watching. Obviously I appreciate people if you would like and subscribe, comments, and if you want to go to GitHub, you can find the code for this project there, as well as my thesis and the full review. Thanks for watching, and I'll see you in the next video.